In question number 16, the equation of a wave is given as y is equals to a cos square 2 pi n t minus 2 pi xy lambda. We want to find the amplitude, frequency and wavelength of this wave. First we have to convert it in this basic equation. So convert this cos square into power 1. So cos square theta can be written as 1 plus cos 2 theta by 2. So y will be a by 2 1 plus cos of 4 pi n t minus 4 pi x by lambda. So the amplitude will be a by 2. Comparing this with 2 pi f, we can write 2 pi f is equals to 4 pi n. So frequency will be 2n. Comparing this with 2 pi by lambda, let's say L is the wavelength, is equals to 4 pi by lambda. So L will be lambda by 2. So amplitude is a by 2, frequency is 2n and wavelength is lambda by 2. So option 1 is correct option. In question number 17, the equation for standing wave is given as 10 sine of pi x by 18 into cos of 84 pi t meter. We want to find the distance between a node and the next antinode. If this represents the wave, the distance between node and next antinode. Node is where displacement is 0 and antinode is where displacement is maximum. The distance between node and adjacent antinode will be lambda by 4. So simply we have to find lambda by 4. Comparing this with k, we can find k is equals to pi by 18 is equals to 2 pi by lambda. So lambda will be 36 meter, lambda by 4 will be 9 meter. So option 2 is correct option. In question number 18, a metallic rod of length 2 meter, this rod is of length 2 meter, is rigidly clamped at its middle point. So this distance will be 1 meter and this distance will also be 1 meter. A longitudinal wave is set up in the rod in such a way that there will be 3 nodes on either side of the clamped point. That means at this side there will be 3 nodes and at this side there will be 3 nodes. We want to find the wavelength of the longitudinal wave. Here note that where the rod is clamped there will be node, and as the ends are open or free there will be antinode at the ends. We want 3 nodes at this side, so drawing the wave we will get antinode at free end. This is one node, this is second node, this is third node and node again at rigid point. Again one node, second node, third node and antinode at free end. So this distance will be 1 lambda plus lambda by 2, that is 3 lambda by 2, plus this distance will be lambda by 4 is equals to 1 meter. So simplifying this, we'll get 7 lambda by 4 is equals to 1 meter. So lambda will be 4 by 7 meter. So option 2 is correct option. In question number 19, it is given that a wave represented by y is equals to a sine of omega t minus kx meets with another wave, let's say y dash, and they produce node at x is equals to 0. Note that means displacement at x is equals to 0 is 0. then what is the equation of this wave y dash? Here, if we draw the graph for this y, it will be like this. And at x is equals to 0, we want net displacement to be 0. So the phase difference should be pi between y and y dash. So y will be minus of e sine omega t minus kx. If this is y, then this is minus y. So option 2 is correct option. In question number 20, we want to find the path difference between two waves represented by y1 is equals to a1 sine of omega t minus 2 pi x by lambda, and y2 is equals to a2 cos of omega t minus 2 pi x by lambda plus theta. First, we will find the phase difference delta phi, and from that we can find the path difference. For that, the both trigonometric function should be same, either sine or either cos. So we'll convert y2 as sine of omega t minus 2 pi x by lambda plus pi by 2 plus theta. As we know, sine pi by 2 plus theta will be cos theta. So the path difference between y1 and y2 will be delta phi is equals to pi by 2 plus theta minus 0, that will be pi by 2 plus theta. Now from the wave, we know that if the path difference is lambda, then phase difference is 2 pi. So for 2 pi phase difference, path difference is lambda. So for the phase difference pi by 2 plus theta, the path difference delta x will be lambda by 2 pi into pi by 2 plus theta. So option 2 is correct option. In question number 21, the equation of wave pulse is given by y is equals to 0.8 divided by 4x plus 5t plus 4. We want to find the amplitude of the pulse. Here amplitude is equals to maximum displacement. If we want maximum value of y, it will be at x is equals to 0 and t is equals to 0. So y will be 0.8 divided by 4, that will be 0.2 units. So option 1 is correct option. In question number 22, it is given that three waves are of equal frequency having amplitudes 10 mm, 4 mm and 7 mm arrive at a given point with successive phase difference pi by 2. The successive phase difference between these two, 10 mm and 4 mm, is pi by 2, and between 4 mm and 7 mm will be pi by 2. We want to find the amplitude of resulting wave. From this we can see that phase difference between 10 mm and 7 mm will be pi. That means 10 mm and 7 mm are in opposite direction, so their resultant will be 10 minus 7, that will be 3 mm. So 3 mm and 4 mm having phase difference pi by 2, so amplitude will be under root a1 square plus a2 square plus 2a1 a2 cos theta. Here theta will be 90, cos 90 is 0. So resultant amplitude will be under root 3 square plus 4 square. That will give us the answer A is equals to 5 mm. So option 3 is correct option. In question number 23, it is given that a standing wave is produced by superimposing two waves. Y1 is equals to A sine of omega t minus kx, and y2 is equals to A sine of omega t plus kx. We want to find the amplitude of particle at distance x. The resultant wave will be y1 plus y2. It can be written as A into sine of omega t minus kx plus sine of omega t plus kx. If we simplify this, we can write A sine of omega t minus kx plus omega t plus kx divided by 2 into cos of omega t minus kx minus omega t minus kx divided by 2. We have used this identity sin A plus sin B is equals to 2 sin A plus B by 2 into cos of A minus B by 2. Simplify this, we'll get 2A cos of kx into sine of omega t. So amplitude will be 2A cos kx. So option 2 is correct option. In question number 24, standing waves are produced in 10-meter long stretched wire, and the wire vibrates in 5 segments. This is one segment, second, third, fourth and fifth. The velocity of wave is 20 meter per second. We want to find the frequency. We can use this relation V is equals to F lambda. So first we have to find the wavelength lambda. From this we can write 5 lambda by 2 is equals to 10 meter. This is lambda by 2 5 times. So lambda will be equal to 4 meter. Frequency will be V by lambda, that is 20 by 4, 5 hertz. So option 3 is correct option. In question number 25, a sonometer wire is given and a stationary wave y is equals to 5 sine of pi x by 25 into cos of 450t is produced in it. We want to find the distance of second and third node from one end. Let's say we are finding distance from this end. As this is fixed end, there will be node at this point. This is first node, this is second node and this is third node. We can see the distance of second node is lambda and distance of third node is lambda plus lambda by 2, that is 3 lambda by 2. From this equation, if we compare this with kx, k will be pi by 25 and k is 2 pi by lambda. So lambda will be equal to 50 centimeter. So distance of second node will be 50 centimeter and 3 lambda by 2 will be equal to 75 centimeter. So distance of third node from end will be 75 centimeter. So option 1 is correct option. In question number 26, it is given that the extension in a string obeying Hooke's law is x, and at this time the speed of sound in the stretched string is v. Now if the extension in the string is increased to 1.5x, what will be the speed of sound in string? The speed of sound in stretched string is given by under root T by mu, where T is tension force and mu is mass per unit length. In both the cases, mass per unit length will be same, so we can write V is directly proportional to root T. Here T is the tension force. Now the string obeys Hooke's law, so we can write F is equals to Kx. So T2 by T1 is equals to X2 by X1, and that is 1.5x divided by x, that is 1.5. So V dash by V is equals to under root T2 by T1. So V dash by V is equals to under root 3 by 2. So V dash is equals to under root 3 by 2 V, that is 1.22 V. So option 1 is correct option. In question number 27, the transverse wave propagating on a stretched string of linear density mu is equals to 3 into 10 power minus 4 kg per meter and the wave is represented by y is equals to 0.2 sine of 1.5x plus 60t, where x is in meter and t is in seconds. We want to find the tension in this string. Velocity can be written as under root t by mu. From this equation we can find the velocity of wave. V is omega by k. This is omega t and this is kx. So omega is 60 and k is 1.5. So velocity will be 40 meter per second. So 40 is equals to under root t by mu. So t is equals to 1600 into mu square. So t is equals to 1600 into 3 into 10 power minus 4. So tension is 0.48 Newton. Option 2 is correct option. Question number 28. A sonometer consists of two wires of length L1 is 1.5 meter and L2 is 1 meter, made up of two different material whose densities are D1 is equals to 5 gram per cc and D2 is equals to 8 gram per cc. Their respective radii are in the ratio R1 by R2 is equals to 4:3. We want to find the ratio of tension T1 by T2 if their fundamental frequencies are equal. That means it is given that F1 is equals to F2. The fundamental frequency is given by 1 divided by 2L under root T by mu. Here mu is the mass per unit length. Mass can be written as density into volume, that is density into area into length divided by L. So mu will be density into area. So this equation will be modified as F is equals to 1 by 2L under root T divided by density into area. As fundamental frequencies for both the wires are same, we can write 1 divided by 2L1 under root T1 by D1A1 is equals to 1 divided by 2L2 under root T2 by D2A2. So 1 upon L1 square T1 by D1A1 is equals to 1 upon L2 square T2 by D2A2. We want to find the ratio of tension forces, that is T1 by T2. It will be L1 square D1A1 divided by L2 square D2A2. L1 by L2 can be written as 3 by 2 whole square. D1 by D2 will be 5 by 8 and A1 by A2 can be written as R1 by R2 whole square, that is 16 by 9. Simplify this, we will get answer 2.5, that is 5 by 2. So ratio will be 5:2. So option 2 is correct option. In question number 29, the velocity of a transverse wave in a stretched wire is 100 meter per second. If the length of wire is doubled and the tension in the string is also doubled, that is L2 is equals to 2L1 and T2 is also equal to 2 times T1, then we want to find the final velocity. Velocity transverse wave in stretched string can be written as under root T by mu. Here we will consider that this mu will remain constant, so velocity is directly proportional to root T. So V2 by V1 is equals to under root T2 by T1, that is under root 2 T1 by T1. So V2 by V1 is equals to root 2. V1 is 100 meter per second here, so V2 will be 1.414 into 100. So V2 is 141.4 meter per second. So option 2 is correct option. In question number 30, it is given that find the ratio of final and initial fundamental frequencies, that is F1 by F2. If length of a stretched string is shortened by 40%, that means L2 is L1 minus 0.4 L1, that is 0.6 L1, and the tension is increased by 44%, That means T2 is equals to T1 plus 0.44 T1, that is 1.44 T1. The fundamental frequency F is given as 1 by 2L under root T by mu. So from this we can write F is directly proportional to root T by L. So F2 by F1 is equals to under root T2 by T1 into L1 by L2. T2 can be written as 1.44 T1 divided by T1 into L1 divided by 0.6 L1. This can be 1.44 square root as 1.2 into 1 divided by 0.6. So F2 by F1 is equals to 2:1. So option 1 is correct option.